Then let's do one more lemma, which is the monotonicity. The claim is that for any f and g being in this simple domain, so simple, measurable, and non-negative, so finite range, non-negative, and measurable functions f and g, such that f is pointwise less than g. So for every input value, we have ordering of this sort. Then the claim is that the integrals are ordered as well when the functions are ordered this way. The proof is not that complicated as before, so let's look at quickly. Let's again note that we can write f actually now when f has this finite range. So let's write f as using the same notation. So we can write f as the indicator. If you look at this, the indicators here, so this we have a partition. So if you plug in any value s, so then s can only belong to one of these AIs. So if s belongs to this precise AI, we get 1 here and 0 elsewhere. So we know that actually this sum can only include one value, and it is A1 if s belongs to capital A1. It's A2 if s belongs to capital A2, etc. So this is why we can represent f as a sum and with indicators in this way. Let's clean this up. I think we looked at this before already. And let's write g in a similar way. Let's also take out the argument. So we think about this as a pointwise combinations of functions. And let's write g in the same way using j from 1 to n. And then these are the possible values of the function g. And then we take the indicators of the bj's here. And we write these functions this way. Then assume that AI intersection bj is non-empty. Then what happens? Then we can pick some point in this intersection. Let's point something called S. So assume that S is in this intersection. We know that then, in this case, the value AI is equal to Fs because S belongs to AI, and that's the only value here. Then we know that F is less than GS because we assume this monotonicity. The value of GS is equal to Bj because S also belongs to Bj. Yeah, it's in the intersection. And then that means that in this case, we have the ordering that AI is less than Bj. Now we can study. With this property, we can study what is the integral of f d mu. And we remember that by definition, it is the sum from y I up to 1 from m, the possible values, and then the measure of AI. This was the definition. Then what? Then we use the same idea with this disjoint events with the union. So we actually write this as the sum 1 from m AI. And then we write this one as the sum of j from 1 to n mu AI in the section bj. Now I hope you recognize the same idea that we did, that these were disjoint across bj, and then this sum becomes the measure of AI. Yep. We rearrange this again, so we have this similar familiar looking thing. We look at these indices I and j, all of them AI, and then the measure of AI intersection Bj. Now what should we do? We want to prove that AI is less than Bj. That's what we are going to want to do. But this is not true necessary for all values. So if you look at f and g, so there could be some values AI which are bigger than Bj's. But if these sets kind of behave in a certain way, so this is possible. AI could be bigger than Bj. So that could be a problem. But on the other hand, we know that for all cases where these are non-empty, if capital AI intersection capital Bj is non-empty, so then this is what we want to do is true. But what if this is empty? What if this intersection is empty? What do we do then? We know that what if this intersection is empty? What's the measure of an empty set? By definition, the empty set has measure 0. So this would give us 0 and we don't worry about the empty set. So actually we write it as a sum of ij pairs such that this aij intersection bj is not empty. Yep. And when it's not empty, so then we can use that, okay, this is less than, here this is less than bj. And that's what we are going to do. So let me just clean a bit here. And we know that it's less than bj, so we can write now bj there in place. And we write here an inequality. Yeah, because these are non-negative values. So if we increase the value here, we get a bigger value for the total sum. Then we actually ignore this condition again. So we know that this remains the same if we also sum over those where we have zeros here. So we can write as the b mu ai intersection bj again. Finally, we rearrange this to the sum where j is first, bj is there. Then we have the sum of I mu ai intersection bj. Again, what do we have here? We recognize that this is just the measure of bj because we have disjoint unions again, and the union is bj. So this is sum 1 to n bj mu of bj. And this is what we defined as the integral of g. And that's the end of the proof of the monotonicity. Let's recall what we proved.